All right, last lesson we talked about optimization of 2D figures. Today we're going to be talking about optimization of 3D figures. So, quick recall for a 2D object, optimize means to find the maximum area or minimize the perimeter. So for a 3D object, if we're thinking about area and perimeter, well, we'd be looking to maximize the volume and minimize the surface area, right? The amount of space it takes up versus the distance around the outside. So our square-based prisms, our first investigation here. Given surface area, determine which square-based prism has the largest volume or contains the most. Each square-based prism below has the same surface area of 24 centimeters squared. Would they have the same volume as well, and determine the volume of each? Well, we know volume quickly to be length times width times height. So in our first example, our length times width times height on this square-based prism would be 5.5 times 1 times 1, which gives us a volume of 5.5 centimeters cubed. Volume on this object here, length times width times height, 2 by 2 by 2, gives us a volume of 8 centimeters. And our third object, we have length times width times height, or 3 times 3 is 9, times 0.5, or halving it, would be 4.5. So they all have the same surface area, but the volume that has the dimensions that have the most volume would be the cube. So the optimal square-based prism given surface area, in order to find that, we have the surface area is equal to 6 times each side length squared, right? That kind of makes sense. Each side length squared gives you a surface area. So if I use my cube example, length times width, or the length times height, so this will still be 2 by 2. So 2 squared gives you surface area here, and there are 6 sides to that whole thing. So 6 times each surface area would give you the surface area of the 3D shape. Or in order to find out the dimensions of that singular side, if you have a surface area, you divide by 6, which would give you s squared. And then in order to find the singular dimension, or one measure here, we take the square root of whatever the surface area divided by 6 would be. So a couple examples here. Determine the dimensions of the square-based prism with maximum volume that can be formed using 5,400 centimeters squared of cardboard. Then determine the volume of the prism. Okay, so surface area is 5,400, and we know that using our surface area would be equal to 6 times each side length squared. 5,400 is equal to 6x squared. Divide both sides by 6. We're finding our s side length variable, so 900 is our s squared, and the opposite operation would be square rooting to get our individual side length, which would in this case be 30. So then the volume would be length times width times height, 30 times 30 times 30, which would be 30, didn't finish that off, 30 cubed. All right. Second investigation. Given volume, determine which square-based prism has the smallest surface area. Each square-based prism below has the same volume, occupies the same amount of space, or contains the same amount, which in this case is 64 centimeters cubed. Would they have the same surface area as well? Determine the surface area of each. So my first example here, the tall pillar looking one, well, if I want to calculate surface area, which would be, if I'm thinking about using some kind of like wrapping paper, for example, I'm wrapping a present, how much paper do I need in order to get all the way around this 3D present? Well, I need the surface area of the bottom here. I need the surface area of this side. I need the surface area of this side, and then the top, and then the other two that are on the back. So if I calculate the surface area of this base here, which would be 2 times 2, I'm also adding it to 2 times 16, which would give us this side. And then I'm also adding this 2 times 16, right? This green line is also 16 centimeters. That gives us a surface area of the base, a surface area of this side, and a surface area of this side. Now that doesn't cover the whole object. There's still 3 other sides. So in theory, we only really covered half of it. So if we have these calculations, what we essentially need to do is double it. So I would then have to multiply everything by 2. So I'd still have 2, and then I'd perform the math here. This would be 4 plus 32 plus 32. So 4 plus 32 plus 32 would be 68, and then 68 times 2 gives me 136 centimeters squared. The cube that I have here, right, we have length times width times height. We know the volume, we're trying to find the surface area. So all I'm really going to do is simply take each side, so 4 times 4 squared, and there are 6 sides on a cube, 6 times a side length squared, which would give me 96. So then the surface area is 96 centimeters squared for this cube. And then my last one, very similar to the first one, I have a length, a width, and a height. I need to add them all. I need to find the surface area of each individual side and then add them together. So we have 5 by 5, 5 by 2.56, and then 5 by 2.56. And then there are 3 more sides like that, so I'm doubling it. So I end up getting a surface area of 101.2 centimeters squared. So the optimal square base prism formula would be our volume is equal to the side length cubed. In order to find the side length and we're given the volume, we simply take the cube root of the volume to give us our side length. So determine the dimensions of the square-based prism with the minimum surface area that can hold 375 millimeters cubed. Then determine the surface area of the prism, right? So it's asking us, okay, find the minimum surface area that can hold this much, and then what is the surface area? So we have our volume. We know in order to find our side length, our individual side length, it would be side length cubed. So I take the cubed root of our volume to give us our individual side length, which would get 7.21 millimeters would be a side. I know that surface area is 6 multiplied by the side length squared. Well, in this case, our side length is 721 squared times 6. 6 times 51.98 would give me 311.9 or 312 millimeters squared for the surface area. So when we talk about cylinders, what must be true about the dimensions of optimal cylinders? Well, if we think about a cube, I'm just going to quickly draw it. A cube has the height, the length, and the width, terrible drawing, all the same length. So we want things to kind of be the same dimensions for every side of that object. Well, when it comes to a cylinder, we want essentially the height to be the same as the diameter. So the distance from one circle to the other versus the distance across the circle are going to be the same. So when the diameter is equal to the height of the cylinder, those would be the dimensions of an optimal cylinder. So the dimensions, if we're actually going to write them down, 2 times the radius, which actually gives us our diameter, and that's what we're looking for, right? Diameter is equal to height. 2 times the radius is equal to our height, or diameter is equal to height. So formula for optimal cylinder given surface area. So if I'm looking for surface area, I know that I need to calculate 2 pi r squared, right? That's the base. And then I'm adding 2 pi r times height. So I know that my h can be substituted with 2r. So I have 2 pi r squared plus 2 pi r multiplied by 2r. As I keep going, 2 pi r squared plus 4 pi r squared, right? I just take 2 pi r times 2r, right? This operation right here. I end up getting 6 pi r squared. So the surface area for the optimal cylinder would be calculated by 6 pi r squared. And this is just showing how we got there. Formula for the optimal cylinder given volume, a little bit shorter, when our volume is equal to pi r squared times our height, which in this case, we know our height can be substituted for 2 pi. So if I take this formula, pi r squared times 2r, Well, now I have 2 pi r, and then r to the exponent 2 times r to the exponent 1 gives me r to the exponent 3, or 2 pi r cubed. So these formulas are only for optimal cylinders. So we have the surface area formula and we have the volume formula. And we have 2 more examples. Determine the dimensions of the cylinder with maximum volume that can be made with 600 centimeters squared of aluminum. All right, so that's surface area. What is the volume of this cylinder? Okay, so we've given our surface area. We're looking for the dimensions to hold the maximum volume. So my surface area, 600 is equal to 6 pi r squared, right, my surface area. I need to isolate to find my radius length, so I divide both sides by 6 pi. 31.83 is equal to r squared. In order to isolate singular r, or the r of degree 1, I take the square root of 31.83. I end up getting 5.6 as my r value. Now, since my height is equal to 2 times my radius, and I know my radius, my height is equal to 2 times, well, we just figured it out, 5.6. So I know that the height of this cylinder is going to be 11.2, right? So the dimensions, my radius is 5.6 and my height is 11.2. I'm looking for the volume. I know to calculate the volume of my optimal cylinder is 2 pi r cubed. 2 pi, my r is 5.6 cubed. This whole expression, I cube this first. I end up getting 1,103.3 centimeters cubed for my volume. Final example, determine the least amount of aluminum, surface area, right, wrapping around something, required to construct a cylindrical can that holds, or with a 1,000 centimeter cubed capacity. So there's our volume, and this was essentially asking us for our surface area. So I'm given the volume, I know my formula to be 2 pi r cubed. I'm trying to find that dimension of r. That's what I can find, right? So I divide both sides by 2 pi. I end up isolating for r cubed, which is 159.23. Taking the cube root of both sides, I end up getting r and 5.4 as my radius. So again, radius is 5.4 centimeters. Therefore, my height, multiply this whole thing just by 2, 10.84 centimeters. So then the surface area, I know my formula 6 pi r squared. I know my r, I can plug that value in now. 6 pi times 5.42 squared gives me a value of 553.73 centimeters squared. So the takeaways from this lesson would be, when you read the question, determine what it is it's asking of you. So this one here, determine the dimensions of a cylinder with maximum volume made with 600 centimeters squared of aluminum, right? So we're looking for surface area and then find what we need to find and then plug it into the other equation. Same idea down here. Let's look at what it is we need to find, determine the least amount of aluminum, and we're given a volume, we're given a capacity. So that's the hint. Use our volume, find our dimension, and then plug it into